Hello, thank you all for coming. I hope you all had a good break. Yeah, we're just gonna get started. For those of you I didn't see at open house, or for those of you who weren't here last semester, this is Sigma. This is the Sig for math and algorithms. So yeah, our goal here is just like to be a community for people who are interested in the more theoretical side of computer science, because wasn't another Sig that did it before us. So yeah, our second semester, first semester went really well. To all the new people, hello. To all the old people, hello again. And yeah, we're just gonna start. I'm gonna introduce like the officers and such, and then we're just gonna go into some stuff about Fibonacci, which is but yeah. Yeah, let's just introduce the officers. Oh, hold on. Actually, no, they don't need a camera. Okay. Cool. Yeah. I'm Anakin. So I'm the president of this whole thing. I'm the helm of the ship. So I'm actually not a CS major. I'm a math major. Before I did anything with Sigma, I've done a lot of stuff with the Sig Pony, mainly cryptography stuff, and then just helping out with a lot of logistics stuff. Some of you may recognize me from being a CA for 173, and then this semester 475, and then in previous semester 374 and 124. And then I like teaching. And then I also do research with Sam. All right. Speaking of Sam,
I did Amazon last summer. I'm one of the officers here as well. I currently am doing like PL course development through CA 374. I'm CA 473. I'm doing some theory research with Zariel as well, and theory research with Anakin. I am also trying to pull grad students and professors to talk at Sigma. That will be exciting to have this.
Hi, I'm Lou. I am also a computer science major. I've also done a lot of teaching. So I worked with CS 125 for a while, and then I did 374. And currently I am over at 225. Not to ramble, but we are kind of revamping the whole like 128, 225 pipeline right now, and it's very interesting. And lots of opportunities for more theory content. But yeah, so I'm graduating senior, and then after this, I'm working in I forgot I wrote that, but yeah.
Aditya's not here, so I'll introduce him. He's one of the other founders of this club. He's interested in like both math and hardware kind of stuff. He does some cool like quantum research, and he's CA for 391. So if any of you guys take that, you'll run into him. And he's into a lot of stuff like functional programming, lots of programming languages, compilers, cryptography. He does a lot of cool stuff, and he seems to know a little bit about everything, which is kind of fun to talk about.
My name is Sam. I was also at Amazon summer with Sam. I'm currently a CS major, maybe also a math major. We'll see how that works out. Before Sigma, I used to be, with the Anakin on the Sig Pony crypto gang. And then I'm a 233 CA and a 173 CA this semester. And I work on compilers. If you like compilers, come talk to me.
Hey everyone, I'm Phil. I'm a CS and Ling major. I'm a senior, so I'm graduating soon, sad times. I'm also a CA for 233, so work with the sun ones, which is fun. And I also do CBCom. So if you like game theory, economics and computation, come for me. Definitely not chilling.
What's fun?
Yes.
Yeah. CBCom's super cool. Just check them out. A lot of that stuff overlaps with what we're going to do. So if you want more, check his stuff out. But yeah, that's everyone in the like moderator admin team. We're friendly. Feel free to talk to us about literally anything. But yeah. So the rest of this meeting is going to be kind of like a glimpse into what the kind of stuff we're going to do here, which is gonna be like talking about like various like math and like algorithmic concepts at like high intuitive level, right? I'm not going to throw you with like pages and pages of like proofs and lemmas and theorems and all that stuff. Try to keep it intuitive, try to keep it interesting, and hopefully you all get something out of it. But yeah, feel free to slow me down and stop me if you have any questions. All right. So I'm sure many of you have seen this before. It comes up in math classes occasionally. And definitely if you've done any sort of like theory class where they talk about recursion or induction, it's one of the first examples. So it's a sequence called the Fibonacci numbers. And here are the first few. And really, the way it's defined recursively, so we just have two numbers to start with, 0 and 1. So the 0 from the first Fibonacci number. And then from there, we just add the previous two, terms to get the next term, right? And you can kind of see it grows relatively quickly. But suppose we were interested in computing this number, right? Oh, there's the idea. I introduced you for you.
Thanks.
But yeah. Anyways, so Fibonacci, and you might wonder, okay, how can we actually compute this, right? So we could just plug in the formula, and you can write a recursive algorithm for this, just a simple program. And if you want to compute like the 7th Fibonacci number, so how would you do that? So you would, just falling back from the definition, you add the 5th and the 6th Fibonacci number. Well, what are the 5th and the 6th Fibonacci number? Well, to compute the 6th Fibonacci number, you need the 5th Fibonacci number and the 4th Fibonacci number. And how do you compute the 5th Fibonacci number? You need you see the point? You kind of get this branching out, like calls and things that you need to compute, and then they just kind of add back up, and then you eventually get the last result. But you can see that even for a small number like the 7th Fibonacci number, there's a lot of computation that needs to go on, right? You can imagine basically that each of these nodes in this tree is an addition going on. So as I compute more and more Fibonacci numbers, if I want to compute the 8th Fibonacci number, I need to take all of this and compute the 6th Fibonacci number and add it up. So this calculation grows immensely. So if you want to compute these numbers, you might be wondering, how can we do it better? Right? And it's one thing that we study a lot in computer science, right? How can we not only compute things, but how can we compute them as fast as possible? Because these efficient algorithms end up being useful in a large variety of applications. So we're going to take a quick sidestep. We're going to talk about exponentiation. And we're actually going to talk about how does Python, if you ever coded in Python, there's a pow function for computing powers of numbers. And how does Python compute its powers very quickly? We're going to learn that right now, and we'll see how to apply it to Fibonacci. So suppose we wanted to compute x to the 13th for some number of x, doesn't matter, right? So the naive way to do this is just to do 12 multiplications, x squared, x cubed, x to the 4th, x to the 5th, and just keep multiplying the number until we get to the 13th power. However, there's a smarter way to do this. So we'll get to why we do this in a second. But suppose we compute powers like this. We compute x squared, which is x times x. Using that, we compute x to the 4th. And then using that, we compute x to the 8th. So we've done 3 multiplications so far. And then using that, we can compute x to the 13th as just x to the 8th as x to the 4th times x. And so we've done 5 total multiplications, which is a lot better than our 13 multiplications. And so if you want to compute like x to like the 200, we're going to see how we can compute it in a much more efficient way. And we're going to use binary. So we're going to look at whatever power we want to compute and look at the binary, right? And so let's see how we can actually turn this into a concrete algorithm. So 13 is 8 plus 4 plus 1, right? And then if you write it in binary, is 1101, right? And so let's say we have the number 13 written in binary. So how do we compute x to the 13th? So I want to represent this just as a little table. And then with this table, we'll see how we can, like the steps needed to actually compute x to the 13th. So at step 0, our initial result is 1. We're just going to start with 1. And at the end of the computation, whatever's in the result column at the very end is going to be our final result. So I'm going to be reading the bits from right to left. So least significant to most significant. So we have a 1. And since we have a 1, our current power x, which is what we're going to be increasing every time. So it's going to x squared, x to the fourth, x to the eighth. So our current power is x, and we're going to, since it's a 1, we're going to take the previous result and x and multiply them together. And we're going to get x. And then we're going to square that. So we're going to get x squared, and there's a 0. But since there's a 0, we're going to square it, which we're going to do every time. But we're not going to actually multiply a result. So we still have x. And then in the third step, we have a 1 in the as our bit. So we're going to take x squared, square it again, and get x to the fourth, and then do x times x to the fourth and get x to the fifth. And then as our last step, we have a 1. And we're going to do the same thing. We're going to square x to the fourth, get x to the eighth. And at the end, we're going to get x to the 13th. Does the algorithm make sense?
What's bit?
Like the current bit that we're so like binary. So we have 13 written binaries. We're looking at each bit. Each digit in binary is referred to as like a bit. It's like the 1 is the first one, and then the 0 bit, and then the 1 bit. So you can see how this is that binary number.
So why the step 2, the bit for step 2 is 0?
Because if you write 13 in binary, it's 1101. So that just comes from converting the number from decimal to binary.
So the 1 represents 8 to the power x to the power 8, and the next one represents x to the power 4.
Yeah.
Like this.
Mhm.
And then we don't have terms of x to the power 2, so it's 0.
Yeah. Right, because 13 is 2 cubed plus 2 to the fourth plus 2 to the 1, or plus 2 to the 0. Yeah. Algorithm makes sense? Right? So if we were actually write this in code, right, and just pseudocode, not any programming language, but you could implement this in your favorite programming language. If someone told me to compute how to compute powers, this is what I would do. I would just, from 1 to n, if I want to compute x to the n, I would just keep multiplying my number by x, and I would just return the result at the end. But what Python does is that they actually do what's called this square multiplication algorithm, where they're doing this repeated squaring over and over, and it's just running through the algorithm. So you convert the number to binary, and you just read the bit, and when the bit is 1, we update our result, and at every step, we just keep squaring. And at the end, we're going to return our result. So this is just what we did in the previous table, just actually written in code, right? And this is actually how Python, when you use the pow function, computes powers, and it's much faster. If you actually do, and for those of you who know big O running time, this left one will take n order of n multiplications, and the right one will take log base 2 of n. And if you graph those things, you'll see that log base 2, logarithms go extremely slow. So even for large n, this is a really efficient algorithm. All right. And so our whole goal was to compute Fibonacci. And now I'm talking about powers. Why is that? Well, so now we're going to bring in just a little bit of like linear algebra and some matrices. We'll see it all come together. So I can just write these two equations. So the nth Fibonacci number is the sum of the previous two. And then also the previous Fibonacci number is equal to itself. So we just have these two linear equations. And what we can do here is we can just represent this as matrices. So this is what you do in, for those of you who do linear algebra, right? And if you're not familiar with linear algebra, this is just matrix multiplication, where you can imagine multiplying this by these two. So you can do f to the n, so the n minus 1 Fibonacci number times the n minus 2 Fibonacci number. You can add them together, and you'll get the nth Fibonacci number. And then similar here, you get the n minus 1 Fibonacci number. But we know what the n minus 1 Fibonacci number and the n minus 2 Fibonacci number is. It's that same matrix just applied to the previous two Fibonacci numbers. right? And I can just keep going with this. And so I can see that to compute the nth Fibonacci number, I just need to take this matrix, raise it to the nth power, multiply it by this column matrix, and I'll get the nth Fibonacci number. And what did our previous algorithm just compute? Powers. So now we have an extremely efficient algorithm to compute Fibonacci. We've taken this from this awful recursive algorithm and gotten to about just about the fastest algorithm you can get for computing Fibonacci. Yes.
See, we were looking at multiplying numbers, and this is multiplying a matrix, so.
So the algorithm, well, the algorithm we just used didn't actually care. It didn't use any fact that x was a number. X could have been a variable, or it could have been like a float or an integer or some sort of real number, or it could be a matrix. The point is, all we cared about the algorithm is that we can multiply something together, and we can multiply matrices. And so we can use that algorithm to actually get our final result. So does everyone see how these matrices and the previous algorithm allows us to compute Fibonacci really fast? It's actually not that hard of an algorithm to implement yourself. Okay. So this is kind of like some of the stuff that goes on in theoretical computer science. Is we use all these tools from math, and we look at it and see how we can build efficient algorithms. Because often when you take like some pure math class, they're never going to really talk about actually efficiently computing these things. But it's a very natural question. In computer science, you're constantly computing things. So being able to apply these techniques of efficient computation to things in math, and then using mathematical tricks to speed up our computations is kind of the stuff we're going to be looking at throughout the semester. Right. So this semester, we're going to be talking about combinatorics. That's going to be our focus for this semester. And we're going to begin with, in my opinion, one of the most beautiful combinatorial objects in all of mathematics, which you may have seen pictures of before. It's called Pascal's triangle. You may have seen it in like some, if you took like an algebra 2 class in high school and they talk about the little mini probability unit that the state forces you to require at the end of the semester. You do combinatorics, and Pascal's triangle comes up in a lot of very cool places. And so what is it? So it's this triangle, and it's got these numbers, and one way to think about it is I can always, so I just create an outer perimeter of ones, and then I just add up the two numbers above it to get my current number. So how did I get 2? I got the 2 ones at the top. I added them together and I got a 2. How did I get a 3? I took 1 plus 2 and got a 3. How did I get 6? I added 2 3s. Right? You kind of see how this triangle gets built. And it turns out there's a lot of extremely deep mathematics in this triangle. So combinatorics as a subject has been studied for centuries. So Blaise Pascal first talked about this triangle in his book, and he called it the Treatise on Triangle Arithmetic. It was just a book talking about properties of this triangle that he came up with. And it's actually one of the first works on probability theory, interestingly enough. But you can go back even further, and it turns out binomial coefficients were first discussed in India in the 10th century. So Pascal's triangle is related to these mathematical objects called binomial coefficients. And like I said, people have been talking about this stuff for centuries. So there's a lot of really cool and deep history going on here. So this symbol here, this NK with these brackets, is you read it as n choose k. And it's the number of ways to choose k items given n distinct items, right? And it's equal to this ugly factorial mess. That doesn't really matter. We're actually not going to care too much about that definition today. But the point is, this symbol represents the number of ways to choose k objects from a set of n objects. But one cool thing about this is that there's like a dual way to look at this. You can equivalently look at the number of ways to not choose n minus k objects, right? If I have 5 objects, I look at, like, if I choose 3 of them from these 5 objects, that's the same thing as just not choosing 2 of the objects and taking the rest. So, yeah, so there's one cool property about these binomial coefficients. And you actually work out the math using the above definition, you'll see that this is true. So everyone kind of get an idea about what what this object is, like what it represents physically. Cool. So where am I going with this? So Pascal's triangle is actually this. So I take, so like row 0 at the top is going to represent my top number in my binomial coefficient. And I'm just going to run through all the numbers 0 up until I hit the top number as I go along the row. Right? So 0, choose 0. How many ways are there to choose 0 objects from a set of 0 objects? 0. There's one way. You just, it's that, nothing. How many ways are there to choose 0 objects from 1 object? 1. How many ways are there to choose 1 object from 1? 1. And this pattern continues. How many ways are there to choose 1 object if you have 2 objects? You pick either of them. And Pascal noticed a cool property in this triangle. So if we look back at the triangle again, and for whatever reason, you decide to look at it from these weird slanted lines. And I'm going to draw these slanted lines, kind of through the diagonals, and I'm going to just sum up all the numbers I hit. Does everyone recognize that going along the diagonal? So it turns out that Fibonacci appears in this triangle, which has nothing to do, seemingly has nothing to do with Fibonacci. Nowhere did I talk about summing, even the definition of like these binomial coefficients, there's no addition going on. And Fibonacci is talking about adding together numbers in a sequence. And yet it appears here. So my claim is, so if you actually look at which numbers are being summed up, it's going to be n minus k, choose k, summed up from k is equal to 0 to this weird n over 2 at the top. And what those brackets at the top mean is we're going to round down. So if n is equal to 3, 3 divided by 2 is 1.5. It's just 3 halves. So I'm going to round down and I'm going to get 1. Okay? And so if we go back, I'm going to claim that this is going to be equal to the n plus 1 Fibonacci number, whatever this is. And I could sit through like a very long proof of induction. It's actually what I was originally going to do until I found this nicer argument. And just do a bunch of algebra and math and make you sit through it and just be like, ta-da, it works. But one of the nice things about combinatorics, and one of the reasons I wanted to do it for this semester, is because a lot of the properties and a lot of the proofs just come by what are called combinatorial arguments, where we're just going to be looking at different ways to count the same object. And if you look at how to count the same object in different ways, then they're equal, then they're going to be equal, and we've proven this identity by looking at the actual math for counting it in 2 different ways. So, what are we going to count? Staircases. So, imagine you're at a staircase, and for whatever reason, you're wondering, how many ways are there to climb from the bottom step to some step along the staircase if you can only take 2 or 1 step at a time? Right? And this is going to be at the center of how we're going to prove that identity we just looked at. So one way to look at it is we can think of this recursively. If we were wondering how to get up to step n, then we can look at how do you get to step n minus 1, and and then take a single step, or we can get to step n minus 2 and take 2 steps. Skip over 2 staircases, 2 steps. Right? So we're computer scientists, so that the starting step be 0. And let's assume we're on step n for some n greater than or equal to 2. Let's think about how we actually got to this step. So either we took a single step from step n minus 1, right? If we're on step n and we took a single step from n minus 1, or we took 2 steps from step n minus 2. And this is why I want n to be greater than or equal to 2, because I don't want to think about what a negative step looks like. So if we just add up the number of ways to get to step n minus 1, take a single step, and add it to the number of ways to get to step n minus 2, just add those 2 values, we'll see how to get to step n, the number of ways to do it, right? So the nth staircase number is equal to the n minus 1 staircase number plus the n minus 2 staircase number. Does this look familiar? But then how many ways are there to get to step 0? 1, you're already on it. And how many ways are there to get step 1? Well, you can't take 2 steps, you've already passed it. You can only take 1 step. So there's only 1 way to do it. And so the nth staircase number is the n plus 1 Fibonacci number. The plus 1 comes from the fact that the 0th Fibonacci number is equal to 0. So you don't have that. So you look at the next Fibonacci number. So does this proof make sense? Yeah. Oh, okay. Right. So 1/2 of our combinatorial argument. We want to count this object, how many ways to go up the staircase. So now we're going to look at a different way, and we'll hopefully get the other thing we're trying to start with. So what is this other angle? Let's just look at our staircase and pick steps to take 2 steps at a time from, right? So I'm going to say at step 1, I'm going to take 2 steps at a time for n equals 4, and then the other steps I'll take 1 step at a time. Or starting at, or I guess step 0, or starting at step 1, I can take 2 steps at a time, and then otherwise start at just step, and then otherwise single steps. So if we can count the number of ways to place our steps of size 2, then our steps of size 1 are fixed, so there's no choice there. So if we have n steps, how many ways can we place k steps of size 2, right? What are the possible ways to place these steps? There's n choose k, right? But how many possible values of k are there? 5 n steps, right? I gotta place a single, so I can either place like a single step of size k, or I can place either 1 step of size 2, or 2 steps of size 2, or 3 steps of size 2. But if I have like 9 steps, for example, can I place 5 steps of size 2? No, because that'll take me to step 10. We don't have 10 steps. So it's going to be round down. We're gonna round down from n over 2. Okay. And with this, we get our identities. We just have all the number of ways that we can place. That top thing should say n minus k, choose k, not n choose k. My bad. I'll fix that later. Yeah, so the top thing should say n minus k, choose k, because as I place a step, I have less steps too. I can't overlap my steps of size 2, so it kind of takes away options. So we get our identity, right? We just looked at the same object in 2 different ways, and we proved our identity. Nowhere did I use this like a bunch of algebra or a bunch of like long complicated like induction arguments. just counting an object in two different ways, we get our identity. That make sense? All right. Are there any questions? All right. No questions in the chat or anything. I cannot see my laptop from here. I don't want to touch my laptop for fear of breaking the slides.
Okay.
I'll try again. It doesn't matter. All right, if you have any questions, then ask me on the Discord. I'll fix the slides before I upload them. But yeah, that's all. Thank you all for coming. I'll leave you with this quote by the man himself, James Bernoulli. But yeah, I hope that gives you an idea. Oh, yes.
Would you like a cookie?
Of course, yes. Yeah.
Could you bring some?
If you have any questions, ask me in the Discord or ask me after here. But yeah. Hopefully that was cool. Thank you all for coming, and I hope to see you for the rest of the semester.